Hi Twitch, just gonna give it another minute and then we'll get started. Anyone else coming? It's just two people in the inner class. Oh, let's see if Twitch is here. That's right. So people can just go watch on their own time. But then you can't ask questions during the lecture. Well, all right. Let's just get started in that case. All right. Hi everyone. So last week we talked a lot about subtyping, and this week we're going to sort of talk about what arguably is the crown jewels of object-oriented programming. Well, I don't know if you'd call them crown jewels, but certainly they're like the most interesting and most complicated extension we're going to make to our OO languages, and that is generics. And we're going to talk about this in the context of both C++ and Java. So we're going to talk about both templates and generics in lecture today, and specifically how they relate to subtyping, because we actually did this already in Haskell, right? I told you about polymorphism, and the story about polymorphism in Haskell was quite simple. We just said, well, you know, you have these type variables instead, and they can be any type, and we're very happy. And life was simple and easy in Haskell. And we will find that life is not simple and easy here in object-oriented subtyping land, and we will find out why that is the case. So that's what today's lecture is all about. All right, so before we start talking about this, I first need to talk about why in programming languages we actually care about parametric polymorphism. Because in fact, subtyping lets you do something very similar to parametric polymorphism using subtyping. And no, I did not turn on the Zoom recording, so let me go ahead and do that. Hi Zoom. You can also, but I think I've had complete recordings on Twitch, so you can also go check them out there. Zoom's a bit spotty. Okay, Zoom's recording is on now. Okay, so what we've got going on here is why are subtyping and parametric polymorphism similar? Well, let's say that we have a function f, and we want to say that this function works on any type of object. Because that's what polymorphism is all about. It says that, you know, this function is generic in some sense. It doesn't require you to only give it an animal or a point or anything like that. It's saying, hey, anything is possible. And so in object-oriented programming, typically every object you know, is a subtype of some super object we call object, which basically, you know, is the parent class for everything in our system. So if I really want to write a function that can take anything at all I need to do is just write a function that takes, you know, an object as an argument. And because, you know, there is the subtype relation, C is a subtype of object, no matter what, that means that I can pass in any object of type C to the function in question. So you can actually do a great deal of, you know, computation just using these, this, you know, object supertype as necessary. And in fact, we will find shortly that in Java, you know, polymorphism via generics is actually completely erased once you get to the runtime. And so when you're inside the runtime, in fact, all it's doing is, you know, turning these into objects and passing them around. So that's kind of interesting. So when we talk about polymorphism, though, polymorphism lets us talk specifically about what the type we want to be able to vary is. So we would instead have some syntax where we're like, hey, given a generic t, no matter what type t is, f takes in t as an argument. And so you can pass in a y with type c into this function because you just say, okay, let t equal c, and now f is a function that takes in c of x's. So are they just the same thing? Should we just, go and say, well, I've already got subtyping, Billy, so we're not going to buy parametric polymorphism for your language. In fact, this is what Golang said. They said, hey, we've got subtyping with interfaces, and polymorphism is very complicated, so we're not going to add it to the language. Well, Go had to relent, and they eventually added polymorphism they added generics for the language. And the reason for this is because it's actually very not nice to write like generic code using subtyping. So here's like the simplest possible example that reveals why this is the case. So here, I'm just writing an identity function, right? Super simple. It's not really that interesting in terms of like, you would never really want an identity function most of the time, but it's very simple, and that makes the issues that show up very clear. So let's imagine that we're implementing the identity function in Haskell for a moment. So that's the right-hand side of this slide, right? So to write the identity function in Haskell, we just say that, hey, this is a function that takes in A's and produces A's. And so whatever you pick as the A in question, that's what you're going to get out. So if you run, identity function on true, well, true is a Boolean. So, this identity function now takes on the type bool to bool, and you get out a Boolean, namely true, when you do this result. Now, shift your eyes over to the left side of the slide where I've tried to do this with subtyping instead. So with subtyping, what I would say instead is, okay, well, this function takes in some object, and yeah, it can be any object, right? I don't really care what it is. So subtyping is great for that. And then this function returns an object. It has to return an object and not something more specific like bool, because we have no idea what it's going to be. When we had polymorphism, when we had generics, we actually gave a name to the type that we passed in as an argument, A in this example. But we don't have any such name. So we just have to say, okay, well, what is it that I can say about the output? Well, I could have passed in a Boolean, I could have passed in a string, I could have passed in a, cake. So I can't really say very much about it. So I have to say, it can return any object at all. And this is very inconvenient if you're using this code, because when you use the code, you're probably going to want to say, well, I know, because I knew what the argument type was. I knew the argument type was a Boolean. I know that R has to be a Boolean, but the programming language has no idea. It's like, well, yeah, this function id, all it says is it takes in objects and produces objects. Who am I to say that, maybe it takes in the input object and it just tosses it out, ignores it, and always gives you a big pile of garbage as output. Well, then it wouldn't be right to give you back a bool in this case. I have no idea. The type signature doesn't say. And so when you just have that extra information, you have to add a bunch of check downcasts. And this is very, very annoying for typical programmers. So that's why parametric polymorphism is useful in a very short example, but obviously, there's all sorts of things that you end up wanting to use generics for when you're doing serious coding in a language. And I would say the primary use case for generics is for implementing what we call container data types. So these are data types that contain other values, like, an array is a sequence of, objects which we don't necessarily care what their type is. They could be ints, they could be strings, they could booleans, whatever, right? I want to write a single generic array that works for any choice of types. And, in Java, we've got maps and we've got pairs. In fact, these get used in situations where it's not even obviously a container, or it's a very trivial container. It only contains one element, but the class in question still provides some sort of useful functionality wrapping around an object in question. So for example, you can have a reference T or a weak reference T, which is a class that represents, some sort of indirected reference to an object in question. You even have this type class T. And this is a kind of interesting use of generics in Java, where the T in this case is going to be precisely the type of the class that this thing is describing. So if I am working with an object called foo, whose class is called foo, and then I want to get the class object representing foo, I would actually get class open angle brackets foo close angle brackets. And that just gives me a little bit of more type information so that I know, on some of the methods on class that I'm actually dealing with foos and not some generic object. Because if I just had a class, right, the class representing the class of an object, then I wouldn't really know anything at compile time about what that object is. And the deal is same in C++, right? Generics are used all the time in C++ for writing these container structures. But C++ also goes a little bit further. You can use templates, that's what they're called in C++, to also do metaprogramming and specialization in your code. We'll talk about what I mean by that in a little bit. And as I sort of alluded to at the beginning of this lecture, subtyping plus parametric polymorphism leads to a very complicated type system. And we're going to see, in this lecture, basically how people deal with this complexity. So if you're C++, your answer to this complexity is to say, this is terrible and I'm not going to worry about it. And C++ basically punts on the issue. It doesn't really address the problem of what makes a template type safe in any reasonable way. And as a result, you get the very infamous C++ template error messages because you don't know if a template will type check or not until you instantiate it. Java, on the other hand, said, hey, we're the user-friendly language, right? We're going to, make a language that people can easily use. And so they said, okay, when we have generics in this language, we are actually going to extend the type system so that we can type check code that is generics. And they had to do it properly. So it's pretty complicated. It's a very Java generics, when you use them superficially, not so bad. But when you start getting into their dark corners, it can get pretty complicated. And there are also some warts associated with Java generics because like many languages, Java didn't originally come out with generics. They were bolted onto the language at a later point in its life cycle. Okay, so any questions about this intro before we dive into talking about both C++ and Java in turn? Okay, so let's get on to C++ templates. All right, so a good way to get introduced to C++ templates is to contrast them to Haskell polymorphic functions. So here I have a function called swap, and what it does is it takes in two references and it swaps their contents. So, whatever the contents of Rx was, move it to Y, and whatever the contents of Ry was, move it to Y. And so I've written some perfectly nice monadic code in Haskell to do this, right? So I take in some IO refs. Those are one element boxes that point to some value of type A and can get mutated. And then all I do is, this implementation isn't complete, but what I do is I read out the values from Rx and Ry, and then I write back the values. Oh, wow, this code is so bad. Yes. So I need to write it to X, Ry. Yes, write X to Ry and write Y to Rx. You get the idea, okay? So this is how we write a polymorphic function in Haskell, and you can see that we are indifferent to what the type stored inside of the IREF is. So how do we write this in C++? Well, in C++, we have to use another language construct. This language construct is called templates. I'm just going to explain this out in case there's anyone in the audience who has never written any C++ code before. So below we have a normal function definition, right? We have a swap, which takes in a t reference called x and a t reference called y. And then we do some assignment to sort of swap things around. By the way, this is a terrible implementation of swap, and you shouldn't implement your swap this way, FYI. Well, I mean, it's okay. This is okay if these are value types. Anyway, so the key difference here is that we didn't really say what the types of x and y are. Instead, we refer to them by some capital T. And so the prologue on top, template type name T, says that actually this function is generic over all choices of T. And so when you actually call this function, we'll figure out what T is, and that's how we will actually type check and compile this function. I want to point out that these are pretty different, even though syntactically they look similar. So one difference, and this has to do with the type system, is Haskell, we explicitly provided a type signature saying what the polymorphism was, but actually this type signature is unnecessary. And why is it unnecessary? Well, remember our lecture on Hindley-Milner type inference. Haskell has a type inference algorithm, and we can use that algorithm to automatically determine what the most general type for an expression is without having to write any explicit type annotations at all. So that's pretty cool. Contrast that with C++. Well, forget about templates for a moment. You're not even allowed to write functions in C++ without specifying what the types of their arguments are. C++ is not willing to do bidirectional type inference. Now, in more recent versions of C++, you can have C++ infer what the return type of a function is by using this arrow auto construct. But in general, you know, everything has to be spelled out explicitly. And then the generics are no difference. You have to specify that this is a templated function using the template keyword to actually, you know, get polymorphism in this way. There's a question from the class, which is, why do I say the C++ swap implementation is bad? It's bad for reasons that don't matter for today's lecture. They matter more when we will have the ownership lecture in Rust. But the reason this implementation is bad is because when I assign x to ttemp, this is going to do a copy assignment because I didn't move out of x, so the only way, so x is still going to be valid while I also have the copy of temp, and so that will induce a copy. And most of the time when you're swapping, you don't really want to do copies. You just want to move things around. But if I had std move in this, then I'd have to explain what std move is, and that's like a very complicated, thing, which is better addressed on its own when we talk about ownership. There's another difference that I want to point out here, which is that the code that these compile to is also quite different. So in Haskell, this swap function is actually going to get compiled into a single function that works in all cases. And the reason for that is because all values in Haskell, well, all values of kind star, whose type has kind star in Haskell, are boxed values. Boxed values are values that have a uniform data representation. And so because all of our values have uniform representation, I can write a single function in machine code that handles them because, as I said, the data representation looks the same. However, in C++, C++ is very down in the metal, right? So they wanted to make sure you didn't have to pay an indirection cost if you're using a template. So when I say that I'm taking in a reference to some object, I'm actually, honest to goodness, taking a reference to whatever that object is. If I had, for example, taken in the object directly, t space x, then I would get in whatever it is directly. If it was a bool, I would get a bool. If it was a string, I get, you know, however big that struct was for representing the string, plus the pointer to the out-of-line buffer. So what's actually going to happen is to compile the C++ function template, because there might be different sizes involved for the inputs in question, I actually have to stamp out a separate version of the body of the template for every single instantiation that I want to do. Questions about this picture for now? There's a question which is, I would assume Haskell/GHC tries to unbox things when it can, right? Are integers boxed or conses? You are correct. Haskell will try to unbox things when it can. The primary technique that it has to do this is inlining. And inlining is a lot like, what C++ is doing, right? Where it's generating specialized versions of the code. Inlining also is profitable because it lets you generate a specialized version of the code. So let me think. So let's say that you have a loop and it takes in some integers and produces an integer, and inside, you're doing some sort of arithmetic computation. There's this transform called the worker wrapper transform that can basically take the boxed inputs, because that's the ABI for the function, and unbox them and do the computation entirely on the unboxed one. GHC Haskell also supports explicitly specifying unboxed data types. These are data types with a hash in their name, and you can also do that if you know that you don't need these to live on the heap. But yes, if you just write int, that is a boxed integer, and absent any optimization, you will be dealing with that box all the way along. All right, so I said that in C++ templates, the way they work is that you go ahead and stamp out a new copy of the function for any given instantiation with a different type of the function in question. And that actually affects the semantics in C++. So when you write C++ code, that uses templates, you can actually perform operations on the object in question, even though you don't know what type it's going to be. So for example, here is a generic sort implementation, and it takes in a pointer to an array. And inside the sort implementation, this is a bubble sort, how droll. Inside of this implementation, we, read out elements from the array in question. And then there's a typo. This should be a capital A, not a lowercase a. We read out an element from the array, and then we do a comparison between them. Now, if I set t to be an integer, of course, this comparison would work. And if I pass this, set this t to some other class, which defined the less than operator on itself, this code would work. But in general, this wouldn't necessarily work, right? Not all functions, not all types in C++ allow you to say less than on them. So C++ is actually saying something. It's saying that, hey, yes, I'm claiming that this function can be instantiated for any type t, but I'm actually going ahead and using some operations on the objects of type t inside my body. And these operations, they don't get collected up nicely like Haskell type classes did when you use them in the function of the body. Nothing like that. They're just implicit constraints on the type parameter. But the way that C++ is actually going to check that things worked out is, well, it's just going to copy paste this code, replace all the occurrences of t with the type you put in, and then see if this thing type checks, right? And so this is a very lazy way to go about implementing this functionality. It doesn't require you to actually have some notion of what is the interface of a type parameter t. But it's something C++ is willing to do, and people rely on it all the time. And so, whenever you see a template and you don't know what it can take, you basically have to read the implementation to find out, or hope they actually documented it, because the implementation can do whatever it wants, and you have to see what the implementation is actually doing to know what the interface that is being relied on is. So here's another example. So templates don't just let you do that. So I guess, right, the original sin of C++ templates is that they like are willing to produce the code on the fly when you finally know what the type of the function T is. So C++ also lets you do something that we couldn't do in Haskell, and that is specialize the meaning of a template when you are implementing it. So here's an example. So this in this example, I've got my swap function again, and it just goes ahead and swaps x and y, making a full copy of T when I do this swap. Now this is very inefficient because like let's say that I have I want to swap two vectors. If I just run this implementation as I have up here, swapping the two vectors will make a full copy of the vector into the temporary, and then copy it back into y when I'm done. So that's super wasteful. The representation of vectors in C++ typically is, just a pointer to some buffer that lives out there in memory. And so if I'm just swapping the vector t's, I just actually need to swap the pointers to the buffer in this case. And so I can write a specialized implementation of swap that works on vectors instead of t. And so when I call swap, hey, well, technically both templates work, but the vector template is more specific, and so it'll get preferentially used if I actually try to swap two vectors. And this specialization actually, is a little subtle because there's a bunch of different ways you can go about doing it. For example, let's say that I have a class called set. Okay, there's something I want to say about the previous slide, but let me get back to it. So we can also specialize classes in this way. So for example, let's say that we have this class named set, and it's parameterized over the t, which type t, which is what we actually store inside of the function in question. So if I want to say, by the way, I want to give a specialization of set for characters. So like I've got my generic binary tree implementation of sets that work for any arbitrary type t. But if I have characters, I happen to know, hey, I can do a more efficient implementation that is simply, storing the set as a bit vector. I can do that. I can write another implementation of the class set, same name, and say, okay, but I want this to apply specifically when the t is a car. And you have to write this little syntax where you've got the template arguments, and then you specify what the actual specialized class is on the name of the class in question. And so now I still have a uniform API for sets, right? So I have a single API for sets that I can pass in some type. And if I pass in a type integer, it's going to do the normal binary tree thing. But if I say, okay, I want a set of characters, well, now I will get a different implementation. I'll get the implementation here, which is doing bit vectory things. So unlike Haskell, right, where I said the representation was uniform, so when I have a polymorphic function or a polymorphic data structure, the the overall shape of the data structure is going to look the same, no matter if I am storing integers or characters. Because in C++ we're just stamping out new versions of the code every time, I can just say, oh, well, I want to stamp out something completely different when I am talking about characters. And that's fine, right? I have all these copies of the code, and so my copy of the code specifically for characters, I'm just going to fiddle around with that and give it a different implementation in that case. You can also partially specialize templates. So, what did I do down here? Well, I said I can give a specialization when I pass in a pointer type, but I'm not going to say what the type of what the thing the pointer points to is. That's still going to be parameterized in some way. And then I could say use a hash table implementation here. Any questions about this? So one nuance that I want to say about the original slide is that technically this is not specialization. What I've actually just done is I've defined another overload of the function that happens to be more specific. So one of the confusing things about C++ is you've got overloads. Overloads lets you write multiple functions with the same name, and you also have a specialization, as you've seen here, where you can take a template and then say, okay, I want something else different when the template is instantiated in this way. And so typically people will just use overloads for functions because functions support overloads. But if you got a struct, you can't overload a struct in a meaningful way. They're not functions. You don't have a function arguments which you can use to resolve the overload. So specialization in this syntax is especially useful when you're templating classes. Any questions about this? Okay, so in summary, what are C++ templates? They're a compile time mechanism for making code generic. And so when I compile my code, I see how my templates were applied, and I instantiate them based on the static types they were applied with in my compilation. And then once I've actually finished substituting all of the contents in the template, that's when I actually go and figure out what all the function calls, what all the operator calls, what all the method calls actually refer to. So in this sense, C++ templates are very similar to macros, which, the C preprocessor macro also lets you go ahead and take some code and then punch it out multiple times with different settings on the inside. Morally, that's what a C++ template is doing, although it's giving you a much nicer syntax and ability to work with the types in question. And so that's the other really important thing about C++ templates. They're type directed. They work at compile time, but at compile time, you do know what the types of all your values are. And so for example, when you instantiate a template, you pass it a type, and the actual implementation you'll get may depend on what that type is. Another thing about C++ templates is they don't really support separate compilation. So separate compilation refers to the idea that you can compile a generic function once and then have other modules make use of it without having to recompile the function in question. Well, C++ templates don't work that way, right? We said that C++ templates have to get instantiated to the specific type at the call site. And so in fact, the way this works is that whenever you instantiate a template, C++ will just go ahead and recompile the entire template for your particular use case. And then what happens is when you're done and you've got all these copies of the same templates lying around everywhere, C++ will just deduplicate the implementation so that there's only one that shows up in the final binary. But it does have to do all of this recompilation over and over again when you do instantiations. And this is one of the reasons why templated C++ gets the reputation for being a very slow to compile programming language, because you're doing this work over and over again. I would be remiss if I did not talk about the standard template library when talking about C++ templates. So we said that generics were all about writing container types, and in C++ that's no exception. So typically we look to the STL, the standard template library, to find most of the containers that we want to use on a day-to-day basis. These containers were sort of designed with runtime efficiency in mind. So they're actually decently efficient. Okay, hash map isn't. Unordered map is not efficient. Don't use unordered map in real C++ code. But most of them do pretty good, and they don't rely on actually having some sort of boxed object representation. So they will go ahead and try to pack things as efficiently as possible. And there's all sorts of wonky stuff that's available in the C++ standard template library. For example, let's say that you want to merge two sorted lists. generically in C++. So there's a bunch of things that you need to do, right? So you need some representation of the list that you're passing in as an argument. You also need a representation for like how you're actually going to do comparisons on them. So you could say merging two sorted lists is, take in two list ranges, take in a comparison function, and then give you back a new list range that has just that has the elements merged together. And so, to actually write this in C++, you can do a ton of stuff. You can be like, okay, well, I need some input iterator for my first list, and I also need a iterator saying what the end of that list is. And then I need an input iterator for my second list, and I also need a iterator saying what the end of that list is. I need my comparison function, which is going to be some, function. It could be a lambda, it could be a regular function, I don't know. And then this produces some out iterator, which I can actually use to read out the results of the comparisons. So like you can write this in a very general way in C++, but there's an old saying which says that like user C++ and library C++ are two completely different languages. And when you write C++, in normal circumstances, you probably don't need to write library C++. But if you're like writing a generic container, which is expected to work in all situations, that can get pretty hairy, and you need to know a lot about like how all the various bits and pieces of C++ are put together. Okay, one more thing about C++ templates, which is C++ templates support a very interesting mode of execution called metaprogramming. So what do I mean by metaprogramming here? Well, what I mean by metaprogramming is using C++ templates, I can write code, I can write template code that turns into more code when I compile it at compile time. So metaprogramming typically is if we programmers simply write code and then run it, then metaprogrammers write code that writes code that we run. And why is C++ templates something that can be used for metaprogramming? Well, the model, as I said multiple times before, is we first instantiate a template, and then we type check that the body makes sense. And this means you can write templates for basically anything, and you can also look at what the types are to decide what you're going to do, and consequently, actually templates are Turing complete. You can like do any arbitrary computation that you want inside of C++ templates. C++ even lets you, pass in integers as arguments to templates, because that's the kind of thing that's useful if you, for example, want to unroll a loop. So here's an example of computing factorial entirely using templates. Now, it's not the goal here is not to understand everything about the code here, but just to give you a flavor for like what is going on here. What is going on here is I've defined a struct named factorial, and I am going to use this by simply repeatedly instantiating instance of factorial to compute what the factorial is. So how does this work? So I have to define a base case. So when I specialize factorial with the 0 integer as its argument, I define, in this case, I'm defining an enum with a value equal to 1. And then the generic template simply defines the enum to be a value whose value is equal to, factorial n minus 1 times n. And so when I do this, we will actually go ahead and instantiate factorial 4, factorial 3, factorial 2, factorial 1, factorial 0, and the C++ compiler will be able to determine at compile time what the value of value is. And to like show that here, I've allocated an array, which typically you can't do with a runtime value here, just to show that it's actually available at compile time. So that's pretty interesting, and you can go pretty freaking far metaprogramming in this way. And there's also some like kind of nifty stuff you can do with templates. For example, you can write a class where it inherits from two classes, But those classes are actually not specified. They can be passed in as arguments to the templated function in question. And this lets you implement a form of mix-in functionality in C++, where you've got this class, it needs to use some operations like, locking policy and the range policy, but you leave those unspecified and the user of the template can specify them. And unlike virtual methods, which we also talked about earlier and would be another way to implement this kind of functionality, this kind of extensibility has zero performance cost at runtime because remember, C++ will instantiate the template and create a copy of the code with the locking policy and the range policy specialized to whatever it is you passed. So the code will be just as good as if you had manually written in the actual destination type inside the body in question. So yeah, templates are pretty crazy, and anyone who writes, any amount of serious C++ code, you're going to have to deal with templates. Any more questions about templates before we move on to Java? Going once, going twice. All right, so let's move on to Java generics. So obviously Java, like C++, had the container problem. They needed a way of defining data structures that could contain objects generically. And for this example, I'm going to show the data structure stack, which supports pushing and popping. So in Java 1.0, which didn't have generics, this is how you would have to write code that operated on a generic stack. So the stack took in objects, and you could pop out objects from the stack. So in this sense, representationally, you could store anything you wanted in the stack, integers, booleans, whatever. And to use the stack, many parts were seemingly reasonable. You can push a string onto the stack without having to say anything. But when you pop something out of the stack, you get out an object. And so you have to do a checked cast back to strings to actually see that, hey, you got a string in this case. So this is what writing code looks like when you don't have generics. With generics, this code can be dramatically simplified. So let's just walk through this for those of you who haven't written any Java before. So here I have this class stack, and I've added another argument in these angled brackets, which is the type parameter for the object in question. So this is a stack of t's. Once I'm inside the body of the function, I can use this type parameter t anywhere in my method definitions. So I'll say that pushing to a stack takes in a t, and when I pop something off the stack, I also get a t back. So now when I want to allocate a stack, I have to say what kind of stack is. So I'm going to say it's a stack of strings. Giving me a new, stack of strings as t argument. And now I can push and pop with impunity without needing any casts, because we know that the return type of pop is t, which happens to be string in this particular case. And so we know that we get a string back. So this looks pretty obvious, right? Like, what's the problem? So the details, as usual, are what make this very difficult to actually implement and reason about sometimes when you're a user. So let's dig into it. So the first thing that I've said already, but I need to say again, is Java generics are type checked. So if I, for example, write this class where I define a priority queue, parameterized over type t, and then I try inside of one of my functions to do a comparison between x and y, which have type t, this will raise a type error. And it will raise a type error in the definition of priority queue, not when I actually instantiate the priority queue, which is what C++ would have done. So when I'm writing the type checker for Java, I need to be able to type check this situation, even though I don't know what the actual instantiation of t is. Additionally, as a user, I have to make sure that I properly specify all of the operations that I want to use on a type t if I actually do want to use any operations. So that's something that there's extra syntax for, which we will see. Okay. I already talked about this slide. This is just, basic generics on a slide. So before I talk about that stuff, I want to harken back to subtyping, and specifically I want to harken back to the discussion we had about variants for arrays. So last week we talked about subtyping, and I said, hey, Java decided that they were going to add arrays to their language, and they decided they were going to make them covariant, so that if B was a subtype of A, then array of B was a subtype of array of A. And we saw that this was unsound because you could put A's into a B this way in this situation. So this is bad, and we can also do lists with generics. So how come does the same situation happen with the generics? Unfortunately, Java did not make the same mistake with generics. So if I write this code where B extends from A, and then I allocate an array list which has type list B, I cannot assign this B array to a variable whose type is list of A. So although B is a subtype of A, and even array list B is a subtype of list of B. List of B is an interface in Java just sort of generically saying what listy things are. List of B is not a subtype of list of A. We call this invariance. Invariance says that a container type, a type constructor, is invariant if no matter if A is a subtype of B or B is a subtype of A, there's no subtyping relationship on the constructed form of that. So this solves a problem that arrays had, because I'm not allowed to do this conversion anymore, and since I'm not allowed to do this conversion, I can't smuggle A into the function. Oh, there's a typo on the slide. It's neither covariant nor contravariant. Sorry. So it isn't the case that list of A is a subtype of list of B. That would be very strange, but not as strange as you might think. Thanks for the catch. All right, so this invariance makes use of generics in Java sometimes cause some problems. So let's look at one of those problems. So let's say that I am writing a function and it's going to be Java 1.0 days, and I want to print out this collection. So in Java, most things support toString. Object has a toString method. And so I could have written this code like this. I could have said, okay, give me a collection, C, because this is old school Java, there's no generic parameter on it, so I don't know what it is. And then I'm going to go ahead and iterate over the elements in C, printing them out as I go. No problem, right? Seems okay. Now let's suppose that I port my code into the latest version of Java, and now I have support for generics. So I might say to myself, hey, generics are cool. I want to, genericify my code. And you might even have a lint saying, hey, if this collection is expecting a parameter, you have to actually give it. So here's the first step. So print collection is generic in the sense that, it works for any a collection holding any type of object. So I might try very reasonably to say, okay, I have a collection of objects, and then I can just, loop over it and print out, each object once again. And this code will work, as in it will type check. But then when I try to actually use this code, I have a problem. What's that problem? Well, remember what we just said about containers in Java. Containers in Java are invariant. So even though foo is a subtype of object, which it is, because everything's a subtype of object, I can't call print collection with a collection foo, because for me to convert a collection foo into a collection object, collection foo has to be a subtype of collection object. But that's just not the case, because these are invariant. So that kind of sucks. And so they had to add another language feature to deal with this situation. So this language feature is called Wildcards. So wildcards in Java say, well, containers are invariant, so that's kind of a pain. So instead what we're going to do is we're going to give you some special thingy that just says, hey, unlike object, this question mark can match any type. And so when I say void print collection question mark C, now I'm allowed to call print collection with collection foo, because the question mark says that, well, you're allowed to pass in anything. Foo, object, bar, whatever you want. The question mark will take it. It's a lot like a type variable, but it's an anonymous type variable. I don't actually refer to it anywhere else in my program. Now, there's something very tricky that happens on the inside of this function. So because the type of the objects that are in the collection are question mark, I don't necessarily know what they are, right? Like they could be foos, they could be bars, they could be objects, they could be anything. So there's very little I can do with a question mark. I have to, basically say in the worst case scenario, it could just be an object, and like I know nothing more of the object in question. So this code example still works. I can iterate over the contents of C, putting them as objects, but that's only okay because object in Java is a supertype of all types. So no matter how I instantiate the question mark, that's okay. And another way to say what's going on here is that so there's a question which is, can we write a nice get first collection question mark C function that doesn't need casting? And the answer is, well, you can't do it with question mark. Instead, you have to use something else. So Java also supports generic methods. So, these are just like templated methods in C++, where you have to, where you can instead explicitly say what the type you want to parameterize over is, and then you can refer to it. So your get first collection question mark would instead become T get first collection T. And this works. And one way to think about wildcards is just syntax sugar for the case where you only want to take in the argument and you don't need to sort of refer to it, for example, in the return type. And for some reason, this syntax is not very popular among Java programmers. Well, maybe it is these days. It wasn't very popular when I was writing Java. I guess it was a decade ago. Jeez. And one reason people don't like this syntax all that much is Java is not very smart. And so you have to actually explicitly specify what type you want T to be instantiated with to actually get things to type check. So like if you don't actually need it, which you don't in print collection, people will typically use a question mark wildcard instead, because you can still infer it in this situation. Okay, so I want to talk about another problem that shows up. So wildcards solved one problem that we had, which is that when we were trying to use the generic method as a client, we couldn't actually convert into the type in question. So we put in a wildcard that lets us do the conversions. But there's a reverse problem, which is, what if inside the body of my generic method, I want to support sort of accessing more interfaces. I want to say, hey, you can give me anything you want, but it has to implement, say, the showable interface so that I actually can call the show method on the object in question. And so once again, this is another use case. It's very legitimate. And so we need to add another language feature for this. And this language feature is called bounded wildcards. So it's not that crazy. So what a bounded wildcard, so if a wildcard says any type is okay, a bounded wildcard says any type is okay so long as it is a subtype of the class in question. So in this case, it has to be a subclass of showable. And once we do this on the inside of the function, we can treat the elements of the collection as showables, right? Because we had this constraint that anything you pass into us had to be a subtype of showable. By the way, there's there's a there's the flip side of this, which is question mark super subtype. And this one says, hey, you can give me anything as long as it is a super type of the object in question. This might seem kind of weird and not useful, but I promise you it is useful, and we'll see why very shortly. Let me pause for a moment. Are there questions about wildcards and bounded wildcards, right? So just to like take a step back, where have we been so far? We've been talking about adding these generics to the language, and when we talked about generics, we had to say how it interacted with subtyping. So we said, okay, so generics are invariantly invariant, so we're not allowed to infer subtyping relations from them when we like if A is a subtype of B, we're not allowed to say anything about containers of A and containers of B. But as a consequence of that, we had to add wildcards and bounded wildcards so that we could still use subtypes of containers and pass them into the functions in question. So no questions about wildcard. And okay, there is a question. What are the use cases of the generic methods that covers that bounded wildcards would not? Or why are all of these different ways of doing similar things? That's a good question. So hopefully wildcards versus bounded wildcards makes sense, right? In some sense, bounded wildcards subsume wildcards. Wildcards are just a simplified case of bounded wildcards. And I would say generic methods, you should also think of it that way as well. So generic methods are an even more generalized form of wildcards, where you can just specify the type T. And so you use a wildcard in those simple situations where you don't need that extra expressivity. We're not even done yet. It gets even more complicated than this. Okay, so I want to talk a little bit about another way about thinking about wildcards. So I said that Java says that collections are invariant. So you can't say anything about the subtype when you wrap a collection around a pair of types. And then to recover the ability to do subtyping type things with collections, we use wildcards instead. Well, another way to think about this is that although types are classes in Java are invariant by default because they may support, both getting the things in the collection as well as putting things in the collection. Remember, that was how we caused a type error in our array example, right? We put something in at the subtype, at the super type, and then try to pull it out at the subtype. So although this is invariant, if we were to split the API of this class into the getters and the setters, we actually would be able to soundly allow for variance. So for example, let's take this class called source. Source only lets you get elements of type A. So this class technically could allow for subtyping relationships. Namely, if A is a subtype of B, then source A could be a subtype of source B. Why is this okay? It's because the only way you can interact with A inside of the source is by getting it out, right? So a source that produces only A's is a subtype of a source that produces only B's if you can always use those A's however you want to use them with B's. And similarly, if I've got a class that's like a sink, I can only put A's into it. I can't take them out again. Then I can treat it contravariantly. I can say, oh, well, if A is a subtype of B, then sink B is a subtype of sink A. And if you're in a language like Scala, it actually supports declaration site variance in this way. So Scala will let you say, okay, you're defining a generic class and you're declaring it to be covariant, and I will hold you to it. I will make sure that the only operations that you can put inside this class are ones that return A's and not ones that take in A's as arguments. And so that's certainly one way to go about doing things. But Java actually did it a different way. So they were like, oh, it's too hard for people to, well, let me think. I think Java was like, we don't really want people to like have to put variance annotations on our classes. So we're going to do it a little differently. So we talked about these wildcards, right? These wildcards were a pretty useful way of solving a problem, which is that, hey, when you pass me a function, when you pass me a collection, please make sure the elements inside at least inherit from some class so I can make use of it usefully. In fact, these wildcards do more than that. They allow us to modify the variance of an object as we go. So let's just step through this example. So here I've got my ref and its type is $extends b. So this is a ref that contains elements. I don't know what elements they contain, but whatever those elements are, they always are a subclass of b. So I'm going to call this source. So when I allocate source, this ref is actually covariant. So if I have a ref of type C, I can assign that to source, and that'll give that the type of source is still $extends b, and in fact what is actually inside the class is just a C, and there's no problem because that's exactly what this type says. Furthermore, when I have this source, I can, for example, ask it to give me a get an element out of it, and I can get out a B because everything in it is guaranteed to be a subclass of B. So this is good too. What I'm not allowed to do is I'm not allowed to use any of the methods on ref which take in the question mark in a contravariant position, namely like sync style things where I pass in an object, right? I'm not allowed to put a B into the source. And the type checker will in fact say this is not okay. The rule for what methods are okay when you have a wildcarded object are if you have a wildcarded object which extends some type B, then you're allowed to use any of the ones where the type in question gets returned, but not the ones where you try to pass in that type as an argument to the function. So effectively, what we've done is, without having to actually define source and sync separately, we've taken a ref, but we've narrowed it down so only the source, only the getter interface is usable. And we didn't have to define a new class to do that. We just had to say ref extends b. Questions about this? This is like the key part, and for the homework that has come out, this is the important slide. Let's do another example. So this is the opposite situation. So I said, hey, extends makes sense. And, it's really good for, if I want to pull out objects from the container and, say, oh, they have type B. And then there's this weird super thing that also lets you, say, okay, it has to be super of type of B. Isn't that kind of weird? But it's not so weird when you think about the contravariant, when you think about the sync case. So I can define a sync version of ref where question mark is a super type of B. And then I say, okay, if I define a source where I assign a ref A to it, this is okay, right? Because A is a super type of B. And now, of course, I can't get out elements from source anymore because, well, I don't know if they'll actually be B's, right? They could be A's, they could be, objects. I have no idea. But what I can do is I can put B's into the source in question, right? Because, no matter what, this source is going to be some super type like A or object, where B is definitely going to be a subtype of that super type. And so I can validly pass it in. And so once again, you know, like before, I have my ref interface, but only the put method on it is usable. Well, you can technically call get, but you will only be able to get an object from get. Questions? I'm going to wait a little longer in case there are questions about these two slides. There's a question which is use site variance compared to when else exactly? Oh yes. So the alternative to use site variance is so-called declaration site variance, and that's where you simply annotate the class when you define it, saying whether or not it's covariant or contravariant. And so you wouldn't be allowed to declare ref as covariant or contravariant because it both takes in and produces A's. So you would be forced to write invariant. But if you like happen to write a class which only had the getters or the setters, then you could declare it to be covariant or contravariant. Okay, so I'm done with the like main technical thing in this lecture, but the story is not done with generics. I said that subtyping plus parametric polymorphism means complications. And in fact, we haven't even scratched the surface for how to do polymorphism with subtyping. We've sort of just been like trying to like deal with like all of this wildcard business. But in fact, in Java, there's also a bunch of other things you can do with subtyping. So we talked about parametric polymorphism, where you just have a function that takes in some type t, and no matter what it is, you know, this function will work on it. Well, the generalization for bounded wildcards is bounded polymorphism, where I say, hey, I accept a type t, and this type t has to be a subtype of, say, showable, and then I can actually, you know, write a function like t to string, where inside of the body I can assume that, you know, this function, this t implements showable. So actually, this particular occurrence of t is basically equivalent to the bounded wildcard case we did. So you could just do a bounded wildcard in this case. But then we talked about situations where, for example, you wanted to return t as a return type. And then you wouldn't be able to just use a wildcard. You would have to actually use a generic method. But there's more. So in fact, Java implements an even more generalized version of bounded polymorphism called f-bounded polymorphism. And f-bounded polymorphism is characterized by when you write this subtype relation, you're allowed to refer to the type on both sides of the subtype arrow. So a max function in Java says that I'll accept any type t as long as it is a subtype of comparable t. Why isn't this just a subtype of comparable? Why is it a subtype of comparable t? Well, there are classes in Java where they are themselves interfaces in Java where they are themselves generics, and they're generics for the same reasons we've talked about in the rest of this lecture, which is that you want to be able to write more precise signatures in the types in question. But that sometimes means that you have to actually write these funny looking things where you say, you know, t is a subtype of comparable t. So just to let's just explain for a moment why comparable looks like this. Well, the reason it looks like for this is if you wrote the interface for comparable where you didn't have any type argument, then, you know, the best you could do for saying how to do a comparison is you could say this has to be some sort of comparable other thing that you pass in, right? There's no type you can refer to. But then if you want to implement a class implementing comparable, you couldn't write the natural thing because, as we established in the subtyping lecture, this is an argument to the function. It's in contravariant position. So you can't validly subtype it because this interface said that compare to worked for any comparable. And in fact, the problem is not in foo. Foo should just only have to implement comparisons on foo objects. But this interface sort of promised too much. It said, no. It's not that you only have to implement comparisons on foos. You have to implement them on any possible comparable thing. And so to fix that, comparable has to take a type argument called t, which says what the type you can actually compare against with is. So when you actually implement foo, you say, well, foos are comparable with other foos, and now you only have to implement compare to on foos in question. So now like there's this funny business, right, where you have this interface A, which you have a compare to on A, and you have to show that this is a subtype of comparable A, which is a subtype of compare to A. And that's sort of the crux of f-bounded polymorphism. If you don't think too hard about it, it kind of mostly makes sense, right? You first do the thing where you add the type to the interface so that you get more precise methods, and then you have this interface and it refers to the type, and you're just like, okay, I guess I'll just write this type again when I write my subtyping relation. And so, for example, if I'm writing this max function, I just say, okay, well, I've got a collection of t's, and, what do these t's need to support? Well, I need to support comparisons on them, and, comparable is a interface that takes in the t as an argument. So in the end, I write this code. I say, okay, well, I'll take any t so long as it extends comparable t. And, that's good enough if you just want to write this code. But, it can get even worse. So, for example, with enum, the enum definition in Java, that's, by the way, I'm not going to examine you on this, but I just want to show you like how freaking complicated it actually gets when you have generics and subtyping. So the enum class says that, hey, you can pass in any argument E as the parameter here. So it's sort of motivated by the same concerns that made comparable take in its type T. But by the way, this EU pass in has to actually extend enum E. And why does it do this? Well, it's because inside the implementation of enum, there are some cases where we've got only an E at hand, and we need to be able to assume that it implements the enum E interface. And so this is kind of mind-breaking, but like, it kind of makes sense. But actually, it doesn't. So Hindley-Miller type inference was simple enough. I could assign it to you to implement as a homework. And, inference is decidable. Yes, it's doubly exponential in the worst case, but never mind that. Well, Java's type system is both unsound. So there was this nice 2016 paper basically showing that you could break Java like with a sufficiently nasty program using generics and f-bounded polymorphism. And in another paper in 2016, it was also shown that truly type checking with Java generics is undecidable. Like there's actually no effective algorithm. Your Java compiler is just using heuristics to try to figure things out most of the time. I have an example of how to make the unsound thing go. And let me think. Do I want to do these slides? Okay. There's an example, and you should check out the papers if you really want to know how these work. But basically, the way to show unsoundness is writing a function that coerces an arbitrary type T to some arbitrary type U and have the type checker accept it. And that just means that, there's an unsoundness. There's also a fun example which you can use to overflow your Java compiler, and that shows, there's a decidability problem. Okay, so in the last minute, I just want to talk one last thing about Java generics, which is type erasure. So generics are not templates because they work on a boxed homogeneous representation. And what that actually means is that in the JVM, when they added generics, they didn't need to add generic support to the runtime itself. Instead, they just replace all of the type parameters T with object, and then that's what actually goes on. And they just insert a bunch of casts for all the places where you actually needed a type T. And why did they do this? Well, it's because they had a pre-existing JVM that was untyped, and they wanted to maintain backwards compatibility. They didn't want to add the generics to the bytecode format itself. This leads to some funny business. For example, you can define static variables on classes in Java, but if you define a static variable on a parameterized class, there's actually only one variable even between all the parameterized things, right? And that's because erasure gets rid of the type parameter at runtime. So there's actually only one class here. And similarly, when you write generic code in Java, you can't, for example, construct a new T on the inside because, well, we've lost that information at runtime. We have no idea what it is when we're actually running the code. And so you have to do one of these class T objects to just actually say, I've actually got the class object, so I can do a constructor in this case. And finally, overloading is a concept that's done in the virtual machine, so you're not allowed to overload on different on collections that only differ in their generics because there's no way to resolve this. So these are all examples of how the implementation was done, causing the semantics of the language to be a little less good. So maybe it was a mistake not to add generics to the bytecode implementation. But there you go. That's generics. And I will see you all on Wednesday. There's a question, which is what should the main takeaway from this class be? So the main takeaway is generics and subtyping are really, really complicated. The second takeaway is I'm going to expect you to know how to work variants with subtyping with wildcards. And that's what the homework is going to be about. So it's a little hard to get it all in your brain in lecture, and hopefully the homework will let you think a little more carefully about this situation. All right, thanks everyone.